Okay, hey, welcome back. This is 6.3, polar coordinates. This gives us an alternate way of talking about points in space, or rather here, points in the plane. So basically you're used to using graph paper that looks like little boxes, and you can, so if this is the x-axis and this is the y-axis, you can move around here by kind of, so here's the origin. So to plot the point 1, 2, how would you do that, right? You would kind of move over by 1 and then go up 2, and that would be your point. So you can describe any point on this grid system by using two numbers. One tells you which way to go in the x direction, one tells you which way to go in the y direction. Okay, so this is the rectangular coordinate system. The polar coordinate system also too will be on you can put it in the xy plane, so it's not clear where the xy plane is in my picture. I'll make that more clear on the blue axes. And there's the x-axis and there's the y-axis. Okay, so again, we still have the x and the y-axis, so we'll put it like that. But now instead of using grid, we're kind of using circles and these what they call, I guess, like radial lines, right? Which look like a lot like the lines we use to kind of count around the unit circle. But anyways, this is kind of our new picture, and we can put these little radial lines through here. So instead of having squares, you have like these weird kind of I don't know, these kind of little segments all the way, all throughout. Those little kind of warped boxes. Okay. So how would I designate a point in this new grid system? What you're going to need is a directed distance, and they'll call that R. It's a directed distance. And then an angle, which of course, a directed angle, which they call theta. Okay, so instead of x comma y over here to designate points in the plane, now you're designating points in the same plane, but with r comma thetas. And we'll want to be able to go back and forth between these two, and all that's kind of junk. Okay, so one of the weird things about the polar coordinates is that they're non-unique. Let me just give you an example of one polar coordinate. Okay, so let's say I want to plot the point 3 comma 3 pi over 4. Okay, so 3 pi over 4, it's kind of like you could figure out where that is, right? So I'll go around in yellow. Here's 1 pi over 4, 2 pi over 4, and then 3 pi over 4 is sitting right here, right? So you're somewhere on this line, and you can kind of think of it as extending through the origin. This line here, maybe I should put that in red or something. Here, it's this line here. I'm trying to go over it in red, it's not looking good. So if it's a positive 3, you're going to go and count on the little circles out 3. So you're going to go 1, 2, 3, and this point right here is your 3 comma 3 pi over 4. Okay, but you can also go in the other direction on this line. You could say, well, what about then negative 3 comma 3 pi over 4? Well, you just rotate over to 3 pi over 4 again. Okay, so again, that's this kind of line I'm outlining here. But instead of going in this direction to positive 3, you're going to go on the other side of the arm. Okay, so it's almost like you want to think there's two sides of the arm. Maybe I should put one in a different color, right? So there's the red side, which is positive, and the blue side, which is negative. So negative 3 pi over 4. How do I get to that? I'm going to go rotate 3 pi over 4 and then count backwards 1, 2, 3, And that's this new point, this -3, 3 pi over 4. Okay. So, in the counterclockwise rotation, it's a positive angle, and the clockwise rotation, those are negative angles. And okay, so let's do some more point plotting, shall we? So the first kind of like set of problems in the book, that's all you're doing. So let me copy down the points we want to plot. You could try plot them on your own, or you could just watch along with what I'm doing. Work a lot in radians. You know, throw some degree problems in there. Let's get my polar graph paper set up in the XY plane. Okay. So it looks like I need about 5 circles. And these are just like the tick marks that you would normally do. So the distance to the first circle, I'm assuming, is 1, and then this is 2, and then this is 3. Okay. This is 4. And then 5. And we'll put 1 more on there for the 6. And then I'm going to put these lines through that represent the angles. Okay, so I always just try. Let's put these in blue. Put them in a different color. So, you know, at pi over 4, and then the one at pi over 6, the one at pi over 3. Excuse me. And then again over here. Through the diagonal there, and then right there. Okay, so I should be able to just count around here. You know, this is pi over 6, pi over 4, pi over 3, and hopefully I'll be able to count out the rest of them. You know, this is 0. Right, so what do we have first? -3, 5 pi over 4. So I rotate the 5 pi over 4. I'm going in this direction. So here's 1, 2, 3, 4, 5 pi over 4 is this line right here. And then I need to go -3. So again, there's kind of like the positive part of the arm here. And then there's the negative part of the arm. I'm running out of colors. Put it in yellow here. Okay, so it's negative, so it's going to be on that yellow part of the arm. So you're going to go 1, 2, -3, and that will be the first point. So again, 1, 2, -3, and that's going to be point. I'll just label it with it's problem 3. Okay. Okay, next, pi over 4, -3. So if I rotate the pi over 4, I'm on this line here. Hopefully you can see my mouse kind of moving on it. And then I have to count in the other direction, right? So this is now the positive side, and this is the negative. So 1, 2, 3, and it'll be over here. Okay, so that's problem 4. 5, pi. So I rotate by pi all the way around. It's right here. And then you just count out 5. 1, 2, 3, 4, and it's sitting right here. Okay, so that's problem 5. 1, 45 degrees. So 45 degrees is pi over 4, and then you just go out 1. So it'll be sitting right there. It's problem 12. 3, 7 pi over 6. So rotate 7 pi over 6. 1, 2, 3, 4, 5, 6 pi over 6, 7 pi over 6. Right? And then you go out 3. So 1, 2, 3. That's problem 16. -1, 3 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2 is this arm here. And then you go back -1, so it's right here. This is problem 18. You can have the same. The weird thing about the XY, the weird thing about comparing these two, in the rectangular coordinates, all of the points are unique. Okay? That's not going to be the case over here in the polar coordinates. Okay? Unfortunately, there's multiple representations for plotting points in the polar coordinate system. Now, I didn't say this, but this is section 1, polar plotting points, actually. So the points, these things are not unique. And one way to get another point that's the same is just to add 2 pi to its angle, right? So if you have 5 pi over 4, you can add in another 2 pi, which is 8 pi over 4, and you'll have the same point. Okay? So that'll be -3 comma 13 pi over 4. And if you allow me to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pi over 4, and then 1, 2, -3. So yeah, it's the same point. So it's one way to do it. Another way to do it is to change the sign and add in pi. So you change it from -3 to 3 and rotate it by another pi. So pi over 4 plus pi is pi over 4 plus 4 pi over 4, which is 5 pi over 4. Okay? So if you allow me to, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 is right here. And then instead of going backwards, I go out 3. So 1, 2, 3. And you see I get the same point as point 4. So there's 2 things you could do. You could rotate, and it kind of makes sense, right? You rotate 90 degrees and then just go in reverse from the original point. Or you can always rotate multiples of 2 pi and end up back at the same place. So let me just note that points are not unique here. In particular, first off, if you're given an r comma theta, you can always just rotate the angle around by 2 pi and it won't change anything. So let's say not just 2 pi, but any multiple of 2 pi. So again, there's that n, which represents an integer, which we represent by the letters capital Z in bold. That's why there's that extra little line there, which is just the letter for the number set. -3, -2, -1, 0, 1, 2, 3, etc. Okay. So any multiple, any integer multiple of 2 pi will work. Then the other variation that you could do to get the same point, you change the sign of the r value and rotate the theta over by what turns out to be an odd multiple of pi. So to get an odd multiple, an odd integer, use the formula 2n plus 1. Okay, because if you put numbers in for n, so if you have the formula 2n plus 1, and you start sticking these numbers in there, if you stick in 0, and let's call this a sub n for some reason, if you stick in 0, you get 0 plus 1, which is 1. If you stick in -1, you'll get -2 plus 1, which is -1. If you stick in 3, or even 4, let's try, you get 8 plus 1. The thing is you're always going to get an odd number with this formula, okay, this 2n plus 1 thing. So basically, you know, you're plotting a point in the polar coordinate system here. So let's just pick this point right here. To get the same point, all you have to do is rotate around an odd multiple of pi, or just go by pi, and then instead of plotting positive, you just go negative. So you end up, instead of counting out 1, 2 here, you just count backwards 1, 2, and you end at the same point. Okay. So that kind of causes a lot of issues for us, and it takes a little bit of work to kind of iron out the issues. So here's another question, type question, plot, and then find another representation of the point in between certain intervals. Okay, so plot, first plot, then find another representation. In other words, find another coordinate that's the exact same thing, another representation. And part A, they want r greater than 0, but then theta in between 2 pi and 4 pi. In part B, they want an r value less than 0, and then theta in between 0 and 2 pi. And then part C, they want r greater than 0, and then theta in between negative 2 pi and 0. Okay, okay, so in particular, we'll look at problem number 22, where they have 8 comma pi over 6. We have to find these alternate representations. Okay, so let me graph the thing first. Instead of going by 1s with my circles, I'm going to go by 2s. So this will be 2, 4, 6, 8. Okay. Okay, so part A. Let's plot the original. All right, so pi over 6 is right here, and then I want to go out to 8. So 8 comma pi over 6 is right there. Okay, so part A, they want r greater than 0, but the angle has to be in between 2 pi and 4 pi. Okay, so I should just be able to add 2 pi to pi over 6 in order to get the same guy. So you go 8 comma. Let's go pi over 6 and then add in another 2 pi. It's the same as, if I find a common denominator, 12 pi over 6. So this would be 13 pi over 6, and that should work as well. So I just started here and then rotated around by 2 pi. I should end up in the same place. And that 13 pi over 6 is definitely in between 2 pi and 4 pi. Okay, next. This time they want a negative r value, so I'll go negative 8. And then the angle in between 0 and 2 pi. Okay. So what I will do is rotate by pi units, pi radians, around to here. And then just, instead of counting out positive 8, you go in the other direction on the arm to negative 8. Okay. So what angle is that if I go and rotate by pi? Well, you can count over to like pi over 6, 2 pi over 3, 4, 5, 6, 7 pi over 6. Or you could literally just add pi to pi over 6. Thirdly, then, they want a positive r, so 8, and then in between negative 2 pi and 0. So I'm going to have to rotate in this other direction by 2 pi. So I'm going to go pi over 6 minus 2 pi. Okay, so that would be 12 pi over 6, so negative 11 pi over 6. And that will be greater than negative 2 pi. Negative 2 pi is literally negative 12 pi over 6. So that's greater than that. And then that's definitely less than 0. Okay, so negative 11 pi over 6. Okay. Okay, I supposed earlier then in this section that we want to be able to convert back and forth between polar and rectangular coordinates. It turns out for certain types of applications, it's easier to work in one rather than the other. And in particular in mathematics, there are certain operations we do on formulas where it's easier to work with one over the other, one version over the other. So we need to develop this ability to kind of go back and forth. Polar coordinates are used a lot in astronomy, okay, which may not seem realistic, but you think about all the satellites that we depend on at this point. There's somebody out there doing astronomy, I guarantee it. Version formulas. Okay, so we can go back and forth. The way we've done our polar graph paper, we superimposed it over the XY plane. Okay, so even when we did our graph paper, you can still see where the X and the Y are. Okay, so there should be kind of a way to, here's our point X comma Y. So the y value is this length. And then the x value is basically the length from here to here, right? Okay, in polar coordinates, this thing is given in terms of r comma theta, where r is basically the distance from the origin all the way out to this point here. And then theta is the direction away from the x-axis, which is also known as the polar axis, which I should have noted. The x-axis in this case is the pole. If you're thinking in terms of polar coordinates, they call it the polar axis. And in particular, the positive x-axis is the polar axis, not the entire axis, but just the positive. And on top of that, I didn't mention that the origin in polar coordinates is called the pole. Okay, so this thing is, of course, for us, we know it as the origin, but in the polar coordinate system, it's called the pole. Okay. So what? Okay, I need look at that. What do we have right there? Uh-oh, it's a right triangle. And then we have all this great trigonometry stuff that we've been developing. We should be able to kind of develop some formulas from that. So the first formula I think that's most obvious is just the Pythagorean stuff, right? So x squared plus y squared is r squared. Okay? And that turns out to be very useful. What else? Well, I know the right triangle definitions for like sine and cosine, right? So you could say, all right, sine of theta, let's start with cosine of theta though. Okay. Cosine of theta is going to be equal to adjacent over hypotenuse, right? It's just using the letters that represent the distances from the triangle in my picture. So you can solve this formula for x, and you get x equals r cosine theta. Likewise, you could use sine's definition. Sine is equal to opposite, which in this case would be y, all over hypotenuse, which in this case would be r. And then solving for y, you get y equals r sine theta. Okay. Those three formulas are extremely important. Okay, we'll be using those for our conversions. And then there's one extra formula, which is kind of also used, but not as much. The tan formula, tan of theta is equal to opposite over adjacent. Okay? So it's these three which are kind of the workhorses for us, but we'll also be using this formula from time to time. Okay, okay. You should be able to memorize that all from this picture. If you could draw this picture, you should be able to, figure out or remember these formulas. There should be no issue with having to memorize. Okay, so I think it's important to memorize this picture. Okay, so let's work with converting from polar to rectangular and vice versa. So first, just working with points in the plane. First, I want to go from polar to rectangular, and so problem 35. I have the polar coordinate 2 comma pi over 3, and then I want to convert that into rectangular coordinates, x comma y. First thing I'm going to do is, it's the only thing I'm going to do is go to these formulas up here, and then it's just plug and chug, right? So x, well, look, this is the r, this is the theta. So I'm just going to be plugging into x equals r cosine theta, and then y equals r sine theta. Just plug and chug. So this will be 2 cosine of pi over 3. Of course, we know pi over 3 is 1/2, so it's 2 times 1/2, which is 1. 1 done, 1 to go. This guy then is 2 sine of pi over 3, which will be 2 times root 3 over 2, which is root 3. Okay, pretty easy, right? Let's do one more just to make sure. 36. 2 comma pi over 6. Okay. So x is equal to 2 cosine of pi over 6. That'll be 2 times root 3 over 2, which will be root 3. So it'll just be reversed. Then y equals 2 sine of pi over 6, which will be 2 times a half, which is 1. Okay, so yeah, pretty simple. The other way around, then we use the other 2 formulas. Okay, so there's like 4 formulas. Use 2 for polar rectangle, use the other 2 for rectangular or polar. This is a little more complicated doing this version. You basically want to start with a graph. So going from rectangular to polar. You want your answer to be written as with an r greater than 0, and you always want your theta to be between 0 and 2 pi, okay? Unless they ask for otherwise. Okay, so let's look at 41, sorry. I got negative 2 comma 2. You want to graph it. You may always graph it. That way you don't forget. You know? So it's negative 1, 2, 1, 2. So you're in the second quadrant. Okay. We are going to need what? We need r, and then we need theta. Okay. So what do we have? We have x, and we have y. Okay. So I can use the Pythagorean theorem to get r. Remember, r squared is equal to x squared plus y squared. So r squared will be equal to 4 plus 4. In other words, r squared is equal to 8. In other words, r is equal to plus or minus, but we need the plus version because we want the positive r. So I'll just put plus root 8, which is 2 root 2. Okay. One thing down, one to go. So what about theta? How am I going to get theta? Well, you can use this other formula, tan of theta, and then you're going to have to use an inverse tan, right? Okay, so tan of theta is going to be from the formula is y over x. So in this case, just substituting in, we have 2 all over negative 2, which is negative 1. And then I want tan inverse of negative 1. And it has to be in the second quadrant, right? So tan inverse of 1 is just pi over 4. Okay? Tan inverse of negative 1, the reference angle for 1 is pi over 4, but we want negative 1, so it's either going to be in the second or fourth quadrant. So we plotted it, we know it's in the second quadrant, so it has to be this 1 to 3 pi over 4. Okay, so which is why it's important to actually plot it. Because you wouldn't know if you were in the second or the fourth quadrant unless you did that. Okay, let's look at one more of those. So this is 45. Negative root 3, comma negative 1. And we want to go to, again, polar. Let's plot it and see what quadrant we're in. So negative root 3 is over here somewhere. And then negative 1 is going to go down to here. Let me erase that one. Negative 1 would be right here. So we're in the 1 2/3 quadrant. First use Pythagorean theorem. So r squared is equal to negative root 3 squared plus negative 1 squared. So r squared is equal to 3 plus 1, which is 4. So r must be 2. And then use the tan formula. So tan theta is going to be y value over the x value. Okay, so tan theta is 1 all over root 3. That sounds like a pi over 6 for a reference angle. But we want the third quadrant, right? So theta will equal, this is pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. Okay, and that would be it. Okay, it's a little more complicated in the rectangular to polar conversions. Okay, so that's converting points. Ultimately, we will want to convert equations, okay, which The cool thing about polar graphs is we're going to be able to draw a whole new set of things, okay? A whole new set of graphs. And they're much more interesting than like a quadratic, because you're going to be able to get rose petal flower things. Okay? There's these other things called lemnisons, which are kind of like, there's cardioids. Okay, so cardioids, like cardiologists, it looks like a heart. You can use circles, just a regular old circle. It's pretty easy to do in polar coordinates. Here's a cardioid. Kind of looks like a heart, but not really, I guess. So it's going to be really cool. And we want to be able to go back and forth between polar equations and rectangular equations. So let's take a look at that process. Okay. Okay. So first off, going from rectangular to polar. So we want to start with something that looks like of the form y equals some function of x, and we want to end up with something that looks like of the form r equals some function of theta. Okay. First, what you should try, and I try to give you a program for doing this. So first, try to replace x with r cosine theta and y with r sine theta. And then secondly, try to solve for r. And there's going to be some weirdness here. I just want to warn you in some of these problems, because of the weirdness with the redundancy of the points. Okay, so anyways, let's look at checkpoint 6. This is actually the video quiz question for this section. It should be on, this is checkpoint 6. I don't know the page number, okay. But it is the video quiz question. Okay. All right, so there's two parts to it. Part A, they want you to convert 3x minus y equals 6. So this is the equation of a line in the rectangular coordinates. Let's see what an equation of a line looks like in the polar coordinate system. Right? So this will be 3r cosine theta minus r sine theta equals 6. Okay. You can factor out an r. And you have 3 cosine theta minus sine theta. You want to solve for r. Okay, so you're going to divide both sides by this object. And you'll get r equals 6 all over 3 cosine theta minus sine theta, which looks pretty ugly. Okay, so sometimes that'll be the case, and that's one of the reasons why you want to do the polar conversion. It's because in one system, it's an ugly equation, but if you convert it, then in the other system, it'll be an easy equation. Okay, and that'll be true especially with circles. Part B, by the way, here is a circle. And of course, this is the answer. Okay, if I didn't make that clear. Okay, anyways, part B, this is a circle that's been shifted, so it centers at 0, -1. I want to convert it, okay? So I replace the x, r cosine theta squared, replace the y. This will be r squared cosine squared theta plus FOIL on this guy. So you get r sine theta times r sine theta is r squared sine squared theta. And then you have r sine theta plus r sine theta, so plus 2 r sine thetas. And then 1 times 1 is 1. Okay. You can move the 1 to the other side and get 0. And then you could also factor out this r squared, and you note there's a Pythagorean identity sitting right in front of you. So that will be 1. This whole thing right here is just 1. So you get r squared plus 2r sine theta equals 0. And this is where the weirdness sort of pops up. You'll see in the book they want you to kind of factor it into two parts, like this. So, I mean, if you were solving for r, you would probably want to do this, okay? Don't move the 2r to the other side. Factor it and set each part equal to 0. And then you get r equals 2 sine theta and r equals 0. If you were to graph this thing, and when you graph something, it's not like the graph is time dependent. It's not like it's growing in front of your eyes. When you graph it, you're literally putting all the points down on the paper at the same time. So for values of theta equaling 0, you're going to get r equals 0. Okay? So note when theta equals 0, you're going to get r equals 0. In other words, this equation alone is kind of good enough. It's kind of like when we were working with solving trigonometric equations and we were looking for infinite solutions, and there was a way to kind of take two sets and make them into one if the angles were a good distance apart. It's the same kind of idea here. This is redundant. We don't need the r equals 0 because it's kind of, if you plotted all of these points here, it's going to be good enough. It's going to get r equals 0 as one of your points. Basically, it's the origin, right? That point's going to be plotted whether you use this equation or this equation. So why not just throw this one away and focus on this guy here? Okay. So that's part of the weirdness. That's and this should be a negative. I apologize. That's kind of the weirdness that's involved. Okay. Okay. So that was the video quiz question. Those two parts. We're on video quiz. I forget which one we're on. So 6.1 was the first problem in this section, in this video quiz. It's video quiz homework number 4. Okay, so 6.1 was the first question, 6.2 is the third, 6.3 will be the fourth, and then 6.1 is the first, 6.2 is the second, 6.3 is the third, and then 6.4 will be the fourth question in video homework 4. Okay? Okay, let's move on. Let's go in the other direction now and see how that pans out, going from polar to rectangular. So in these cases, you want to use pretty much anything goes. You use so before we kind of just used those two formulas, but now we're going to use pretty much anything. The r squared equals x squared plus y squared. You could replace r cosine thetas with x. Replace r sine thetas with y. And if you have a tan theta, just replace that thing with y over x, if you can get one of those things. Okay, so basically you're starting with some function of theta, r equals f of theta. So on one side you have an r, on the other side everything's in terms of theta. And then you're moving over to y equals f of x, okay, hopefully. Okay, so I'll look at example 7 from the book and see how that goes. So first one, a is r equals 5. Okay, it's kind of like the polar version of a vertical line, like x equals 5 would be a vertical line in the rectangular coordinate system. So what does this picture look like in the polar coordinate system? What the heck is it? Okay, so let's figure that out. I notice r squared is equal to x squared plus y squared, right? And you may have to do a bit of fiddling around. This isn't something that would be all that easy to do, like for a computer to figure out. But we are supposedly more creative than a computer, so we'll see. So I'm replacing r with 5, and then 5 squared is 25. And I've done it, right? I have I mean, it's something identifiable. I don't need to solve it for y. This is a circle with origin 0, 0 and radius 5. So just leave it in that form. If it's really identifiable, you don't need to solve for y. You know, it's better just leave it this, because you're probably not going to recognize y equals plus or minus square root 25 minus x squared as well. I'd rather have it in this form. So that's kind of going to be our answer. In other words, when you have these simple, look at how simple this equation is in polar coordinates versus what it is in the rectangular coordinates. And that's one of the advantages. And that's why they use it in astronomy so much. When you're dealing with astronomy, you're dealing with a lot of circles. Okay. And the equations in the polar coordinate system are just way easier to deal with. Okay, so anyways, part B, let's kind of look at the other version, right? If that was the vertical line version, what's the horizontal type version going to look like? So theta is pi over 4. I could take tan of theta and set that equal to y over x. In other words, plugging in pi over 4, I get tan of pi over 4 equals y over x. And then I know tan of pi over 4 is 1 equals y over x. And then you can multiply both sides by x. Flip-flop sides. Lo and behold, you have the diagonal through the origin. Okay. So what's really happening is you're kind of rotating over to this angle pi over 4, and you're letting the r value vary over the real numbers. And what happens is you end up graphing out the line y equals x, right? The diagonal through the origin. Okay, so that's kind of neat. What else? Let's look at part C. This is r equals 3 cosecant theta. Okay. So note cosecant is the same as sine, right? Sine theta. You multiply both sides by sine, you get 3 equals r sine theta. That r sine theta, what is that? That's y, right? So this is 3 equals y. So horizontal line in polar coordinates is kind of not as pretty as the horizontal line in the rectangular coordinates. Let's look at one last one. R equals -6 cosine theta. And this one is a little bit more complicated. I'm gonna square both. What am I gonna do? Multiply both sides by r. Okay, so I'll get r squared equals -6r cosine theta. Okay. Then I notice, hey, look at this. R cosine theta is equal to x, right? So you get r squared equals -6x. Then r squared, well, hey, that's equal to x squared plus y squared. And lo and behold, this is an equation of a circle. It may not all that familiar, but if you took pre-calc, you know you can move this over to the other side and then complete the square. Right? So completing the square, you take b all over 2 squared, so in this case 6 all over 2, and then square it. That'll be 9, so you add 9 to both sides. And you get x plus 3 squared here, plus y squared equals 9. So what is this thing? In the polar or the rectangular coordinate system, it's a shifted circle, right? So it's 1, 2, -3, 0, with a radius of 3. And there it is. Okay, so that's beginning. We want to investigate this even further, I believe, in the upcoming sections, and start playing around with different pictures of graphs, plotting different pictures. So we'll get the rose petal thing, the cardioid, and all that neat stuff. Okay. So that'll be in the next section, 6.4. Okay, thanks for watching, and we'll see you next time.